Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we are going to start one new area, that is textile for protection against microbial and viral hazard. So, this is very special type of textile material which are used in extreme condition to protect ourselves from microbial and viral hazards. So, if we classify the protective textiles, as we have all discussed at different modules. So, thermal protection is one type of protection, chemical and biological protection, and mechanical and special hazard type system. So, here we are talking, we have discussed the thermal, chemical protection we have discussed, mechanical protection we have discussed. Now, biological protective systems are also important. So, if we discuss about the protective textiles for antimicrobial hazard, there are different types of microorganisms, pathogens, and along with the different types of chemicals. So, and also in this module we will discuss the protection from the viral threat. So, the basic terminology we will use here, the terminologies are the antimicrobial, which inhibits microbial growth, antiviral, inactivates the viruses, biocidal, destroy the microorganisms, and barrier textiles, which prevents the this microorganisms from penetration. So, any pathogens it should prevent from penetration. Okay. The protection mechanisms are of two types, one is active protection, another is passive protection. So, active protections are by using the chemical and biocidal treatments. What is that? Here the active chemicals will be there, which is antimicrobial agents which kills the pathogen within this system. Okay. And passive mechanisms are that the pathogens are prevented from the penetration. So, dense weave multilayer barriers are there which will prevent it from penetration. So, two ways we can protect ourselves, or we can use active and passive protection system together. So, medical and biological hazards are, so pathogen reservoirs are there, textiles can harbor bacteria, virus and fungi. So, that is the interference. So, in the textile itself it can harbor the bacteria, virus and fungi. Suppose one medical personnel, he or she is moving from one infected room to other room. This person may carry this bacteria or virus to other room. So, for that the textile can harbor this viruses, exposure routes. So, through contact, droplets, aerosol, okay, fluid penetration, and that actually infects. So, that health risks are there, infection spreads and cross contaminations are there. So, if we understand all these threats, okay, interference, we can design the protective clothing accordingly. So, medical textiles for pathogen controls, there are different types of medical textiles available. So, the definition is the textile materials which is designed to reduce the microbial contaminations. The fabric system engineered to provide barrier, filtration and antimicrobial functions. So, it should provide the barrier, it should prevent from penetration and also antimicrobial function, it should kill the bacteria. So, applications are medical garments, filtration fabrics, wound dressings, hospital fabrics. So, different types of protective clothing we can use. The functional requirements are that fabric must provide microbial barrier performance and filtration efficiency. It should prevent the particles from penetration. This filtration efficiency we have discussed in air filtration also, air and water filtration. Mechanical durability should be there. During usage or laundering, the fabric's integrity should be there. Balance between protection, breathability and thermophysiological comfort should be maintained. So, protection should be there, but at the same time it should be breathable or it should be thermophysiological comfortable. So, if we classify the medical textiles, so barrier fabrics for infection control. So, there should be barrier, it should not allow any microbes or virus from penetration. Filtration fabric from airborne pathogen removal. So, the filter should be able to prevent the pathogen, airborne pathogen, and antimicrobial treatment for microbial inhibition. So, classification of fibers used in medical textiles. So, the natural and natural. So, the natural and regenerated fibers are used widely. Synthetic fibers like polyester, polypropylene, polyamides are used widely, very commonly used. Specialty fibers used for advanced filtration fabrics like melt blown fibers or nanofibers are also used. So, cotton fibers for medical application. So, due to the wedge group present here, so it enables the chemical finishing and it is a soft hydrophilic, it can absorb moisture, it is a breathable. high moisture absorption, okay. It is often modified with antimicrobial finishes such as silver nanoparticles, chitosan coating. So, if we normally use some finishes that may sometimes change the moisture absorption. Polyester fibers are used for higher strength and hydrophobic in nature it is so which reduce the liquid penetration, and it is used for reusable medical garment during, because its durability is there because of the high melting point. Polypropylene fibers are used in medical textiles. So, due to its low density, so this is widely used for non-woven medical fabrics, highly hydrophobic, okay. Its moisture again is almost 0% and commonly used in melt blown filtration filter fabric for medical mask. So, fibers surface chemistry is, so functional groups OH, COOH, NH to influence the fibers wettability and microbial inhibition interaction. Surface chemistry controls the addition of antimicrobial coating and nanoparticles. So, modification methods includes plasma treatment, graft polymerization, sol gel coating. So, we can modify the surface also by using plasma treatment, graft polymerization and sol gel coating. So, fabric structure we can classify that woven fabric structures we can use knitted and non-wovens, all different types of fabric structures we use, okay, that in there will be controlled pore size, and non-woven fabrics for due to the random fiber network it has high filtration efficiencies are there. So, woven fabrics for medical textiles. So, warp weft interlacement produce the staple which produces stable pore geometry here there and high fabric integrity. So, there will be stable pore geometry because fabrics are not that stretchable in lengthwise and widthwise direction. The pore geometry will be stable, does not change too much, like in knitted fabric it is highly stretchable, the pore geometry gets changed with a small load. So, barrier properties are influenced by thread density. So, if we increase the thread density, that means it will be compact, the pore size will be, pore space will be less. So, barrier property will enhance. So, commonly used in reusable medical protective garments. So, this woven fabrics are basically used for reusable, so that we can use repeatedly, but non-wovens are normally used for disposable medical textiles. So, knitted fabric structures are also used. So, loop structure provides elasticity and flexibility. So, knitted structures are used basically for bandages, compression fabric, wearable medical textiles. So, large pores require antimicrobial finish for infection control. So, here antimicrobial finish is required. This has least barrier property. So, non-wovens are also used, this produced by mechanical, thermal or chemical bonding techniques. So, fiber diameters typically 1 to 20 micron, widely used in medical masks and disposable protective fabrics. Spun bonded fabrics are also used, that is non-woven fabrics, continuous filaments produced by the polymer extrusion in the spinning. The continuous filaments are, they form the web and then subsequently they are bonded, fiber diameter range 15 to 35 micron. So, use as outer layer in multilayer medical fabrics like spun bonded is normally very commonly used in along with the melt blown and spun bonded. So, spun bonded gives the protection of the actual filter layer of melt blown non-woven. Melt blown ultra fine fibers are there, that basically from 1 to 5 microns fiber with pore size between 1 to 10 micron. So, provides filtration, bacterial filtration 95 to 99%. So, bacterial filtration efficiency 95 to 99%. So, fabric cover factor is also important for bacteria and virus protection. So, cover factor can be calculated, it is correlated with the yarn linear density. So, fabric thickness and density, medical fabric thickness is typically 0.2 to 1.5 millimeter. So, higher density improves the protection capability. So, it must balance the filtration with air permeability. So, air permeability should be between 50 to 300 millimeter per second. So, fiber diameter we can change for to control the filtration. Smaller fiber increases the surface area and particle interception. This detailed we have discussed in the filtration. For any virus and bacteria we can trap using the smaller fiber surface. So, with the which provides higher surface area and that entrap the virus and bacteria. Okay. So, nanofibers also can be used which enhance the particle capture. Filtration efficiency increases as the fiber diameter decreases. So, filtration efficiency equation, as we know all this equation like upstream and downstream particle concentration, based on that we can calculate the filtration efficiency. So, multilayer medical fabrics. So, medical fabrics often consist of different layer. Outer layer is barrier layer, okay. Then filtration layer, absorbent layer and then comfort layer. So, this outer barrier layer which prevents the any outer like water to penetrate, even it prevents the bacteria and larger particles are there, and the main filtration layer which actually filter out the the virus and bacteria. So, each layer contributes to barrier filtration and comfort performance. Layer arrangements affect overall protective performance. So, outer layer, it is basically hydrophobic fabric, repels the water droplet and contaminants. So, any contamination of bacteria and virus, it will repel, okay, and along with the water droplet. So, due to the hydrophobic nature, so surface treatment enhance the fluid repellency, maintains structural durability. Next layer is filtration layer. It is mainly produced from the melt blown or nanofiber membrane, nanofiber web used for particle capture. So, these particles are basically here in this present context, it is a virus or bacteria, it captures. High fiber density improves the filtration efficiency. So, electrostatic charge can enhance the particle enhancement, particles capturing. Inner and comfort layer, so which improves the thermophysiological comfort, which is in contact with the body, our skin, that absorbs the moisture and sweat, maintains wearer comfort during prolonged use. So, surface wettability is important. So, to test if we want super hydrophobic, so material, so that contact angle should be more than 150, which is required. So, surface wettability determines the fluid repellency and microbial attachment. So, antimicrobial mechanisms in textiles are, so passive barrier mechanism, okay, where and contact killing the antimicrobial surface. So, one is passive barrier mechanism, another is contact killing antibacterial antimicrobial surface. Third is controlled release of antimicrobial system, and metal ion antimicrobial activities. So, these are the different mechanisms in the textiles which kills the bacteria, and reactive oxygen species ROS mechanism. So, let us see all these mechanisms. So, passive barrier mechanism is actually dense textile structure prevent the physical penetration of microorganism. So, if we can create the dense structure by oven or non-oven material, so there the particles that the microorganisms, maybe virus or bacteria, they will be physically stopped, okay, physically prevented from penetration. That may be different types of filtration mechanisms are there that we have already discussed. So, electrostatic charge we can also create to enhance the capture efficiency. Then contact killing antimicrobial surface. So, in the surface what we do, we treat with the different types of antimicrobial treatment like silver particle, silver, copper, zinc oxide, okay, different types of particles we treat the outer surface. This is a contaminated surface where there is no treatment. Now, the antimicrobial coating is created at the outer surface when any microbes like bacteria comes into contact. So, microbial cell membrane will get damaged, then cell death will take place. Okay. The applications are hospital surface and different public places, medical devices, even food packaging. We can use this type of contact killing antimicrobial surfaces. Then next process is that controlled release of that antimicrobial agent. So, controlled release antimicrobial system, where the release of antimicrobial agents are there. So, antimicrobial agents diffuse slowly from the polymer matrices. So, within the polymer matrix the antimicrobial agents are there, it will slowly get diffused, provide long term antimicrobial protection, and this antimicrobial agent can be encapsulated, okay, and then it is that the capsule can be coated with on the surface, and there will be controlled release from the capsule, and this release is controlled by, governed by the fixed diffusion law. Next is metal ion antimicrobial activities. So, silver ion binds to thiol group in barrier protection, inhibiting the enzymatic activities. So, DNA replication is disrupted by metal ion interaction with nucleic acid, and this is the example of this. So, this is the example of the reaction. Next is that reactive oxygen species. So, ROS mechanism, ROS species such as superoxide or hydroxyl radicals which damage the microbial membrane. Okay. And this oxidative stress leads to protein oxidation. So, protein and lipid peroxidation. Okay. So, these are the basic reaction. So, antimicrobial materials in textiles which are used, silver nanoparticles, copper based antimicrobial system. There are different types of antimicrobial agents we can treat on the textile material. I mean chitogen based antimicrobial textiles are used, very common, and these are used by pad dry cure method, sol gel coating technology, plasma surface treatment, layer by layer deposition, in situ nanoparticle formation. So, this functionalization on the textile surface are done using all these technologies, even electrospinning for nanofiber membrane on the textile substrate, that we can do. So, pad dry cure method is a very conventional method. Then sol gel techniques are used, so which produces thin organic hybrid coating. Then plasma surface treatment. Plasma introduces functional group onto the fiber surface. It improves adhesion of antimicrobial coating. enables environmentally friendly surface modification. So, it increases the hydrophilicity, adhesive properties. So, different types of properties are improved. So, its application is medical devices and implants. So, layer by layer deposition. So, at different layers we can deposit the chemical during coating. This is the substrate. Okay. So, negatively charged layer followed by positively charged layer. So, sequential adsorption of oppositely charged polymers or nanoparticles are deposited, produces nanoscale multilayer coatings which allows precise control of functional layer thickness. Next is in situ nanoparticle formation. So, metal ions reduce directly on the textile surface to form nanoparticles. So, on the textile surface, okay, nanoparticles are created there, in situ deposited. So, this is the one example reaction. So, it improves the nanoparticle adhesion and durability. So, as because it is a in situ deposition is there, it is created. So, electrospinning nanofiber membranes, we have already discussed the electrospinning processes earlier. So, it produces high porosity, large surface area, tunable fiber diameter. We can change the fiber diameter, which is these are used for medical filtration, medical drug delivery. So, cell culture and scaffold, energy storage. So, different applications are there, but in present case we can use this for bacteria and virus protection. So, performance evaluation of materials. So, antibacterial testing method, antiviral testing we can use, log reduction calculation, wash durability assessment, mechanical testing of medical textiles. So, for medical textiles which are used for virus and bacteria protection, we should go for all this through all these tests, breathability and pressure drop test. So, antibacterial test method, here we use ATCC 100 quantitative antibacterial test, ISO 9000, ISO 2074-3 standard, which is for textile antibacterial antimicrobial activity. These are based on reduction in bacterial colony count. So, before with and without the antibacterial textile material, we can count the growth. Antiviral testings are there, that is ISO 18184 evaluates antiviral activity of textile materials. So, viral titers are measured before and after the textile exposure. So, untreated and treated. So, reduction in viral plague. So, this is antiviral agents. are actually, this is the textile is treated with that, and before that is untreated one and treated one. So, reduction in cell damage. So, results expressed as log reduction value as per the ISO 18184 system. So, log reduction calculation, this formula is there. So, where N0 is the initial microbial count and N is the surviving microbial count. So, this using this equation we can calculate the log reduction. Higher log values indicate strong antimicrobial performance. Wash durability assessment, repeated laundering cycle with simulating the different practical uses, and after that we can test the antibacterial activities. So, before wash and post wash assessment we can do. So, there we can test the wash durability assessment. This evaluates the retention of antimicrobial activity. So, mechanical testing of medical textiles are also important. So, we do tensile testing, tear testing, tensile tear, tensile strength ensure the structural integrity, and tear resistance prevent the barrier failure, and fabric durability is critical for reusable medical textiles, particularly for woven or knitted textiles. Breathability is also important. We do by the air permeability, pressure drop across the medium, and also the water vapor permeability we can do. So, medical textile applications are wide. So, surgical gowns we can use, medical face masks, isolation gowns, hospital bedding, antimicrobial wound dressing, surgical drape, medical cap, head covers, shoe covers, sterilizing wraps, impermeable medical textiles. So, wide applications are there where antiviral and antibacterial that textiles are important. So, antibacterial, antimicrobial patient clothing are there. The surgical gown, it provides actually the sterile barrier against the microorganism like bacteria, virus, require fluid resistance and breathability. So, fluid resistance is important to prevent any external fluid like blood or any fluid, contaminated fluid from penetration, but at the same time it requires breathability. Often manufactured from multi-layered non-woven fabrics. Medical face masks we have all discussed in the air filtration in detail. So, it utilizes melt blown fabric, it achieves high bacteria filtration. So, electrostatic fiber enhance the particle capture efficiency. Isolation gowns are there where protect healthcare worker from biological fluids where there is a chance of any fluid. So, this type of isolation grounds are used, designed with liquid barrier coating. So, available in disposable and reusable forms, hospital bedding and curtains. So, antimicrobial treatment is required. So, antimicrobial treated fabrics reduce the microbial persistence. So, the fabrics here in this hospital room should be antimicrobial treated. Frequent exposure to contaminated environment is there. So, functional finishes helps in reducing the cross contamination. So, where we need to have functional finish. So, antimicrobial wound dressings are important to provide most moist wound healing environments, because in the wound dressing that it will be it is a moist conditions there, microbial growth chances are there. So, that chances of microbial growth is there. So, we have to design the wound dressing accordingly. So, release antimicrobial agent to prevent the infection. So, this wound dressing will have its within the structure, the antimicrobial agent will be there. This antimicrobial agent will get released gradually to prevent any infection. So, it is often composed of biopolymer fiber and nanofiber mat. The surgical drapes are there used to cover the patient and equipment during the surgery. So, these are the surgical drapes and provide sterile barrier protection against the pathogens and fluids. So, these are often made of SMS structures, spun bonded melt blown and spun bonded non-woven structures. So, medical caps are important to prevent hair and scalps microorganism from the contaminating sterile environment. Lightweight spun bond fabrics are used here. Designed for breathability, comfort during long surgical procedure. Shoe covers are also important, protects the sterile areas from microbial contaminations against the carried by the footwear. So, shoe covers are used. It is basically they are laminated or coated nonwoven fabrics, provide liquid and puncture particulate barrier properties. So, this there will be some treatment will be there, like our water repellent treatment are normally there. So, that it liquid penetration is reduced. Sterilization wraps are used to wrap the surgical instruments before autoclaving. Implantable medical textiles are there, like vascular grafts, different types of hernia mesh, artificial ligaments. So, these are also used, and where the antimicrobial treatment are important. Antimicrobial patient clothing, hospital garments treated with silver, chitosan or different other compound. So, those are used for patient clothing. This helps reduce hospital acquired infection HAI. So, from hospital the patient should not bring any other infection. So, for that antimicrobial or antiviral fabrics are required. So, it provides comfort, hygiene and repeated wash durability. Typically, these fabrics are of oven structure. So, sustainability in medical textiles, important. Environmental impact on medical textiles are basically bio based antimicrobial materials should be used, and reusable material textiles, medical textiles should be targeted, so that environmental impact is reduced. We should use recycling process if possible. So, potential release of nanoparticles during washing, chemical residues may affect the aquatic ecosystems. So, whatever dangerous chemicals are there, that if we wash during wash, that may affect the aquatic ecosystems. Sustainable finishing technologies are to be adopted. Bio based antimicrobial materials we should adopt. People are, so plant derived compounds such as the essential oils and polyphenols are used for antimicrobial treatment on textile material. So, biopolymers including chitosan alginates are used, so that to reduce the environment effect. So, renewable alternatives to synthetic antimicrobial agents are required. So, reusable medical textiles, durable antimicrobial finishes can be used, and that will be protected, that will actually be effective for repeated use. So, which will reduce the environmental burden compared to disposable PP. So, we should target to use the reusable durable product, but the one precaution we should take extreme precaution, so that the cross contamination should not be there. Requires robust wash stable functionalization technique, so that the material, that antimicrobial finish should not come out after washing. The future research and innovations include the smart antimicrobial textiles, multifunctional textile system, and future direction in medical textiles. So, these are the areas in future research. So, smart antimicrobial textiles are, so stimuli response coatings, that is by activated by light, temperature and humidity. Then self cleaning surface using photocatalytic materials, integration of sensors for pathogen detection. We can use some sensor which will detect the pathogen. Multifunctional textile systems combining filtration, antimicrobial activity and comfort. So, we should design this type of PPE, that protective equipment, hybrid fiber structure and advanced nanomaterials. Hybrid fiber structure and advanced nanomaterials can be adopted. So, we can optimize the structure for different medical applications. So, smart fabrics for textiles. So, color changing fiber, temperature regulating fiber, shape memory fabric, waterproof and breathable fabric. So, all these different types of smart integration can be there in medical textiles. So, development of sustainable antimicrobial materials, smart medical PPE with integrated protective functions. And we have come to the end of this session, and in the last session we will discuss that the protection from the automobile using the airbags, which is a very specialized textile product. So, till then, thank you.